In this video, I'm going to show you how to test for linearity. The three examples we're going to look at are the three examples from our in-class activities. The first one is y of t is equal to x of t squared. Again, there are two tests that you need to do for linearity. The first one is additivity, and for that you can say that you let x of t equal the sum of x1 of t plus x2 of t. You then put that through your system. In this case, where there was x of t, you replace it with x1 of t plus x2 of t. So y of t is equal to x1 of t plus x2 of t, quantity squared. Now, I'm squaring a sum, so I have to distribute that inside it. So I end up with x1 of t squared plus, that's squaring the first term. Squaring the second term, you would have x2 of t squared, but you also have the cross terms. x1 times x2 multiplied by 2. So, this first term would be y1, the second term would be y2, but there's no way to get rid of the last term, so there's no way to manipulate this to end up with y of t equals just y1 plus y2. Therefore, and that's the symbol for therefore, not linear. Alright, now I could stop there, but just to show you that it works, you can also look at the scaling property. For that, you let x of t equal some constant a times x1 of t, and the goal is to show that y of t is equal to a times y1. When you put this a x1 of t in where you had x of t, you end up with y of t equal to a x1 of t quantity squared. But now when I square this, I end up with a squared x1 of t squared, which is not equal to a times y1 of t. So again, it is not linear. Okay, now for the second example, we have y of t is equal to x of minus t. Basically, y is just the time reversed version of x. So again, we're going to let, for additivity, sorry about that, we let x of t equal x1 of t plus x2 of t. Then y of t is equal to, again, this is what I'm plugging in, but now to time reverse, the only place that there's t's are here and here, so I time reverse each of these. So y of t is equal to x1 of minus t plus x2 of minus t, which is y1 of t plus y2 of t. So it passes the additivity test. Now let's look at scaling. So remember, to be linear, it has to pass both of them. If it fails either one, then it's not linear. So scaling, I'm going to let x of t equals a times x1 of t. Now when I put that into the system, the only places the t is inside here. I time reverse that and I get that y of t is equal to a times x1 of minus t, which is equal to a times y1 of t. So it passes. Scaling. Since it passes scaling and it passes additivity, it is linear. Right. Now the last one, for additivity, I'm going to let x of t equal x1 of t plus x2 of t. I'm going to write additivity up here. Now, again, I place these into the system. Now the system input is x, so everywhere there was an x, I replace it with x1 plus x2. So I have x of t minus 3. So x of t minus 3 is x1 of t minus 3 plus x2 of t minus 3. So then y of t is equal to t times x1 of t minus 3 plus x2 of t minus 3. Now, to make this look something like y1 and y2, I have to distribute t over the sum. I end up with t times x1 of t minus 3 plus t times x2 of t minus 3. Well, that is y1 of t, and that is y2 of t. So it passes additivity. Now let's move over here a little bit. To determine the scaling, whether it passes scaling, again I'm going to let x of t equal a x1 of t. Again, something I see a lot of students is they try and make this start to do the system. You're just saying let x be a scaled version of something else, right? Don't apply the minus t or the t minus 3 yet, okay? Now I put this into the system and I get y of t equals a times x1 of t minus, a times, forgot the t, t times a x1 of t minus 3. Alright, now I'm not quite done yet. I have to do one little change, which is I have to commute the t and the a, because I want a times something, and that something hopefully is y1. So if I commute the t and the a, I get a times t x1 of t minus 3. Sorry about that. and this part is in fact y1. So it passes. And it's therefore linear. It is linear. Alright, so that's it for those 3 examples.